Picture a smooth landscape floating over the flat plane. At every point you stand on, the ground is at some height. Right here, near the origin, that landscape could take one of just a few shapes. It might be a ball opening upward. It might be an upside-down dome, or a saddle, rising one way, falling the other, like the seat of a horse. Every one of these surfaces is written by a single compact expression, x transpose, A, x. Learn to read it, and you can glance at a matrix and name its shape. That reading is called definiteness. So let's build this expression from scratch, in 2 dimensions, where we can see everything. Take a matrix A and a vector x with 2 components. Notice x transpose is a row on its side, A in the middle, x standing as a column. Row times matrix times column. The result is a single number. Multiply A into x first. That gives a little column. Then the row eats that column. Multiply it out term by term. 2 products added together, and it tidies into this. A times x1 squared plus 2b times x1 x2 plus c times x2 squared. A pure degree 2 polynomial. That is why we call it a quadratic form. One thing to fix in mind. From here on, we assume A is symmetric. The off-diagonal entries match. That's why a single B feeds both cross terms and shows up doubled. Then everything works cleanly. Here is the key idea, and it's a picture. Treat x transpose AX as a height above each point x. As x roams the plane, that height traces a surface. When the form is always positive, it's a ball, lowest at the origin. Flip the sign of everything, and the ball turns over into a dome. Now the form is always negative, the origin the single highest point, the ground falling away everywhere. But the most interesting shape is neither. Make the form rise one direction and fall another, and you get a saddle. Walk one way and you climb. Turn 90 degrees and you descend. So the whole question becomes, which shape does a matrix draw? The answer hides inside it, and there are 2 clean ways to read it out. Definiteness is just names for how x transpose AX behaves. Strictly above 0 everywhere is positive definite, the ball. Strictly below 0 is negative definite, the dome. Allow equality and you get the semi-definite cases, where the form may graze 0 but never crosses. And when it takes both signs, it's indefinite, the saddle, the case that trips people up. Here is the first way to read the shape, and it is beautiful. For a symmetric matrix, the definiteness is decided entirely by the signs of its eigenvalues. If every eigenvalue is positive, the form curves up everywhere. A ball, positive definite. If every eigenvalue is 0 or positive, positive semi-definite, with a flat direction wherever 1 equals 0. If every eigenvalue is negative, it curves down everywhere. A dome. And the moment the signs are mixed, you have a saddle. Indefinite. That single mixed sign is the whole tell. Why do the eigenvalues rule everything? A symmetric matrix has perpendicular eigendirections, and along each, the form is just that eigenvalue times a square. Positive, the ground rises. Negative, it falls. The lambda signs are the curvatures. There's a second test that needs no eigenvalues, often faster by hand. It reads the leading principal minors, the determinants of the top left 1 by 1 block, then the 2 by 2 on down the diagonal. For our 2 by 2, the first minor is just the top left entry A. The second is the full determinant, AC minus B squared. Now the rule, Sylvester's criterion. If both minors are positive, the matrix is positive definite, a ball. If the signs of the leading minors alternate, first negative, then positive, it's negative definite, a dome. The alternating pattern is the fingerprint of downward curvature, and the quickest tell of all. If the determinant D2 is negative, The two eigenvalues have opposite signs, so the matrix is indefinite, a saddle. No further work needed. Let's classify a real matrix. Here is a with 2, 1, 1, 3. It's symmetric. The off-diagonal entries match, so both our tests apply. Take the minor test first. The first minor is the top left entry, 2, positive. The second is the determinant, 6 minus 1, which is 5, also positive. Both leading minors positive. By Sylvester's rule, that alone tells us A is positive definite, a ball. Let's confirm it the eigenvalue way. The trace is 5, the determinant is 5, so the characteristic equation is lambda squared minus 5 lambda plus 5. The quadratic formula gives 5 plus or minus root 5 over 2, about 3.62 and 1.38. Both strictly positive, positive definite. The two tests agree. And here is the surface it draws. 2x squared plus 2xy plus 3y squared. A genuine ball curving upward everywhere. Exactly what positive definite promised. Now a matrix that looks harmless but hides a saddle. A with 1, 2, 2, 1. Symmetric again. So let's read its shape. Jump straight to the determinant. 1 times 1 is 1, minus 2 squared, which is 4. That leaves minus 3. The determinant is negative. A negative determinant in a 2 by 2 means the eigenvalues must have opposite signs. So without another step, we already know. Indefinite. A saddle. Confirm with eigenvalues. 1 minus lambda, all squared, minus 4 equals 0. Expand and it factors into lambda minus 3 times lambda plus 1. The eigenvalues are 3 and minus 1. 1 positive, 1 negative. Mixed signs. Indefinite, just as the determinant told us. And its surface x squared plus 4xy plus y squared is a true saddle. Along 1, 1, 1 the form climbs. Along 1, minus 1 it plunges. The origin is a mountain pass. One more gem, because it comes up constantly. Over all unit vectors, length exactly 1. How large and how small can x transpose Ax get? The answer is startlingly clean. The maximum is the largest eigenvalue, the minimum the smallest, and each extreme is reached when x points along the matching eigenvector. The reason is our earlier identity. On unit vectors, the form is a weighted average of the eigenvalues, and an average always lands between the smallest and largest. Make it concrete. Say A has eigenvalues 5 and 2. In the eigenvector basis, the form is 5y1 squared plus 2, y2 squared, which tidies to 2 plus 3y1 squared. As y1 squared runs 0 to 1, it sweeps from 2 to 5. Your turn. Here is a matrix G with all 4 entries equal to 1. Pause the video and classify it. Ball, dome, saddle, or something in between. Use whichever test you like. Here's the walkthrough. The first minor is 1, but the determinant is 0. The minor test lands on the boundary, not definite. The eigenvalues confirm it. 0 and 2, nothing negative. Semi-definite, not indefinite. And the cleanest view, x transpose gx is x1 plus x2 all squared. A square is never negative, but hits 0 whenever x1 equals minus x2. So it's positive semi-definite. If you name that, you've got it. Trap 1. Forgetting symmetry. The eigenvalue sign rule assumes A equals its transpose. For a non-symmetric matrix, symmetrize first or it doesn't apply. Trap 2. Confusing definite with semi-definite. If even one non-zero x makes the form 0, it's not positive definite, only semi-definite. Definite means strictly above 0. Trap 3. Trusting the determinant alone. A positive determinant only says the eigenvalues share a sign. Both could be negative, a dome. You still need the first minor, trap 4. Dropping the length constraint, the clean Max-Sandman lives on the unit sphere. Without fixing the length, doubling x quadruples the form. No finite maximum at all. Let's gather it all. A quadratic form is x transpose A. X, a surface over the plane, a x1 squared plus 2b, x1 x2 plus c, x2 squared. Its shape is set by the eigenvalue signs. All positive a ball, all negative a dome, mixed a saddle. Definiteness in one line. For a fast check by hand, the leading principle minors. Both positive means positive definite. No eigenvalues required. And on the unit sphere, the form is trapped between the smallest and largest eigenvalues. Hold those four lines, and any symmetric matrix reveals its shape at a glance.